All right, so let's put everything that we talked about in this chapter together and start talking about finding the pH of an acidic or a basic solution. We're going to start with the strong acids this time. So here's our first one. We want to know what is the pH for this solution for a 0.020 molar HCl solution. So in order to do this, we have to start with Bronsted-Lowry acid-base reaction. So you've got ACl plus water is going to be in equilibrium with H3O plus and Cl minus. Okay, and then these are going to be aqueous. Now, one thing to point out right away, okay, I use the equilibrium sign because this is a practice that we're going to get into because this is most of the reactions are going to be in equilibrium. However, HCl is a strong acid. That's why you got to know that list of 6 strong acids, because once you know those strong acids, you know exactly that this reaction is going to go all the way to completion. So ideally, at the end of this reaction at equilibrium, there should be no HCl left. Okay, so let's try this out. So if the initial concentration of HCl is 0.020 molar, okay, that means you're going to have a concentration of 0 molar for H3O plus and 0 molar for Cl minus. The change should be that you should go down by 0.020 molar for HCl, and then the concentration of H3O plus is going to go up by 0.02 molar, and the concentration of Cl minus is also going to go up by 0.20 molar. Okay, so that way at equilibrium, there's going to be no concentration of HCl left, and it's all H3O plus, which that concentration is 0.020 molar, and Cl minus, which is also 0.020 molar. Okay, so now in order to solve for the pH, we need this concentration, the concentration of H3O plus. So knowing that value, we can solve for pH, which is the negative log of the concentration of H3O plus, okay? And we know that the concentration of H3O plus is 0.020 molar. So if we pop that in, the pH of this solution should be 1.70. Okay, pretty straightforward. Let's see if we can try this problem again. This time, let's do it with a base. So here's our problem, okay? Let's find the concentration, or let's find the pH of 0.0000040 molar. So let's simplify this. This is actually 4.0 times 10 to the minus 6 molar. That's a lot easier to deal with than writing out the waters. Okay, and it says that you can ignore the OH from water. All right, so here's what we got. We're going to start by writing an equation again. So you've got NaOH, which is aqueous, is in water. It breaks down. Now, since this is going to be a strong base, it's going to dissociate completely. So it's going to split apart into sodium ion and OH minus. Okay, so initially, you know the concentration is 4.0 times 10 to the minus 6 molar. You're going to have no concentration of sodium ion, no concentration of hydroxide ion. Okay, chlorine, the change, chlorine. The change, because this is going to go all the way to completion, so the dissociation is going to be close to 100%. The concentration of sodium hydroxide is also going to go down by the same value, 4.0 times 10 to the minus 6. So that way, at equilibrium, you're going to have no concentration of sodium hydroxide left. But that also means that the concentration of sodium ion is also going to go up by 4.0 times 10 to the minus 6. Concentration of hydroxide ion will go up by 4.0 times 10 to the minus 6 as well. All right, so at equilibrium, we know that the concentrations of sodium ion and hydroxide ion will be 4.0 times 10 to the minus 6 molar. So from that value, we could plug in and find POH. because that's going to be the negative log of hydroxide ion, and that's the value that we do have. So if we pop that in, so for the concentration of hydroxide ion, we know it's 4.0 times 10 to the minus 6. The pOH of this reaction would be 5.40. Now, to get to the pH, all we have to do is take 14 minus the pOH, which we know is going to be that value, 5.40. The pH will be about 8.66. Okay. So yeah, that's how you do it. So this can be one. This is one step more complicated because we have pOH instead we had OH instead of H3O plus, and we had to figure out a way to convert between the two. Now here's one more. Let's get real crazy now. All right. So what if you had calcium oxide? Is calcium oxide going to act as an acid, or is it going to act as a base? And what is the pH? Now we're going to get a little bit more into oxides in the next chapter, in the next section. Okay, but for right now, just to whet our appetites, let's see how calcium oxide behaves in water. So calcium oxide, which is a solid, reacts with water. Okay, and it's going to produce calcium 2-plex. Okay. And we know, so if calcium 2 plus goes on its own, what's left over is the oxide. So you know that the proton from the water, because calcium oxide doesn't have it, the proton from the water has to go to that oxygen. So you end up forming 2 hydroxide ions. Okay. Now, by definition, since acid is going to be your proton donor, so that means water is going to act as your acid. Calcium oxide, in this case, would be your base. Okay. So, that being said, if we're going to create an ice table for this, initially the concentration of calcium oxide, according to this problem, is going to be 0.010 molar. And you're going to have no concentrations of the products. The change is that calcium oxide is going to completely dissociate because it's an ionic compound. So it's going to go down by 0.01 molar, but calcium 2 plus will go up by 0.01 molar, and the hydroxide ions are going to go up. In this case, because you have 2 hydroxides, it's actually going to go up twice as high, so 0.01 times 2, or 0.02. Okay, so at equilibrium, you're going to have no concentration of calcium oxide. You're going to have a concentration of 0.01 molar for calcium 2 plus, and then you're going to have a concentration of 0.02 molar for hydroxide ion. So with that being said, we can solve for pOH because that's the negative log of the concentration of hydroxide ion, and we know that value. We just pop it in and solve for pOH. So that value comes out to be the negative log of 0.020 molar is 1.70. And if we take pH, if we're solving for pH, we just take the pOH minus 14. Okay, pOH 14 minus pOH, that will give us a value of 12.30. So this is a pretty basic ionic solid. Okay. All right. Now at this point, we've done between this video and the previous video, we've calculated, we've taken the concentration of H3O plus and found pH. We've taken the concentration of a strong acid and found pH. We've taken the concentration of strong base and found pH, including a wrinkle if you've got an ionic salt like we did. What if, let's do one more problem. What is the concentration of H3O plus if the solution if the solution has a pH of 3.60? Okay. So what I'm saying is this, and then I'm also looking for the concentration of hydroxide ion. Okay. So what I'm saying is this: It's going to be a little bit of a two-step process. One process is to do this. Let's go with the hydroxide ion first. We know that pH plus pOH is going to be equal to 14. And if we know that the pH is going to be 3.60, we can pop this in, okay, and solve for pOH. So pOH would be equal to 14 minus the pH, which is 3.60. This is going to be equal to 10.40. All right. Now we know that the pOH is equal to the negative log of the concentration of hydroxide ion. And to solve for pOH, and to solve for the concentration of hydroxide ion, in order to do that, we're going to take 10, raise it to the negative pOH, and that's going to give us our value. So if we take 10 raised to the negative 10.40, that's going to give us a concentration of hydroxide ion, which in this problem, that concentration is going to be, it's going to be 3.98 times 10 to the minus 11th molar. Okay. So that's one. Now, the other thing that it's asking us to do is to find the concentration of hydronium ion. All right, so that one's a little bit more straightforward. We know that the pH is 3.60, and that pH is equal to the negative log of the concentration of hydronium ion. And so if we're solving for the hydronium ion concentration, that's going to be equal to 10 raised to the negative pH, like we did in the previous problem, except instead of pOH, it's pH. So this is going to be equal to 10 raised to the minus 3.60, or that concentration of the hydronium ion is going to be 2.51 times 10 to the minus 4th molar. And there you go. All right, so all of this stuff, all the problems that we just did, sets us up for the next step, where we try to take a look at the pH of weak acids, weak bases, salts, and once we take a look at those, we can start taking a look at titrations.